Hi everyone, my name is Yang. Today I'm going to talk about our paper, TinyTrain. Nowadays, AI and deep learning is basically everywhere around us. These deep learning and AI capabilities are already deployed on our daily mobile devices or wearables, and they enable diverse and interesting applications around us. For example, object recognition, object detection, classification, and so on and so forth. However, one of the key limitations in the current systems is that once the deep learning models are deployed on edge devices, it is really hard to update them whenever new user inputs are given or deployed environments are changed. But to make our system to be effective for dynamic nature of realistic application scenarios, we really need to enable our systems and deployed models to be adaptive to user inputs or context or domain shifts during deployment. So that's why on-device training has become so essential. But it has unique challenges. First, labeling is difficult because it's hard to get clean and abundant labeled data on device. Second, training is expensive in both memory and computation. As you can see here, Resonate 50 requires almost 3 GB memory with the base size of 8, which can easily exceed the memory limit of commonly used resource-constrained devices like Raspberry Pi 02 with 512 MB of RAM. Even the optimized network architectures like MCUNet require almost 1 GB memory easily. Also, training requires 3 times more computation than inference, so it's computationally expensive as well. Now, let's have a look at the literature in this area. First, naive approach is to only fine-tune the head or last layer. The amount of memory and computation required is minimal, but the accuracy degradation is the largest. Second, tiny transfer learning, TinyTL, it adds live residual model to each block of the backbone network. Then it freezes the original backbone and only update those added blocks. This way, you can save the computation and memory, but it still suffers from moderate accuracy loss. Last is sparse update. This method selectively updates a few layers and channels of each layer so they can save memory and computation. However, it has to identify important layers and channels by going through burdensome offline search processes, which may require testing a few thousand different configurations. So, to address all the challenges and limitations of the prior works, we propose TinyTrain. It has 2 explicit contributions over previous state-of-the-art, which relies on sparse update methods. The first one is during offline pre-training phase, we adopt few-shot learning pre-training method to explicitly cope with data sparsity issue that adaptive system will encounter during deployment. This ensures the high accuracy. Then, during the online deployment phase, we propose the task adaptive sparse update that first identify which layers and channels to update given the target data, memory budgets, and computation budgets. After that, we selectively update those chosen layers and channels on our target hardware. And I'd like to highlight that our selection method process is done efficiently on device, and it has to be performed only once during deployment. So this way, we overcome the key limitation of prior work that it needs to test a few thousand different configurations in order to identify important layers and channels. In more detail, our task adaptive sparse update is based on the observational contribution analysis that accuracy gain of updating a part of the layer shows different patterns when it only considers the accuracy, as you can see on the left-hand side, and when it starts to consider memory and computation, as you can see in the figures in the middle and on the right-hand side. So we incorporate those factors into our multi-objective criterion, and it's also based on our intuition that feature potential can be used as a proxy for the accuracy gain because it tells us how important the layers and channels are. So our multi-objective criterion, which can be efficiently computed on device, enables to identify important layers and channels that can maximize the accuracy without incurring too much memory and computation overheads. Now, let's have a look at the experimental setup. we employed 9 datasets and 5 baselines and 3 different model architectures so that the results can be generalizable. Now let's have a look at the results, accuracy results first. Compared to full train, which indicating to updating the entire networks, TinyTrain achieves up to 5% higher accuracy. And compared to SORA method, which is relied on sparse update method, TinyTrain achieves up to 7.7% higher accuracy. And then regarding memory footprint and computational cost, TinyTrain achieves 987 times lower memory and 7.12 times lower computation compared to full train. And TinyTrain achieves 1.96 times lower memory and 1.65 times lower computation compared to SORA method. After that, we evaluated our methods in terms of end-to-end training time and energy consumption on edge devices like Raspberry Pi 02. And the result shows that TinyTrain achieves up to 11.2 times lower latency and up to 4.2 times lower energy consumption compared to full train. In addition, we performed ablation study to investigate the effectiveness of future learning pre-training component and dynamic channel selection component of our TinyTrain. The results demonstrate that our proposed future learning pre-training and dynamic channel selection shows the robust improvement in terms of accuracy. Lastly, here's the summary of our work. TinyTrain enables adaptive systems through joint optimization of data, memory, and computation that allows efficient on-device training. And as our takeaway messages, first, future learning pre-training is effective in ensuring high accuracy because it explicitly copes with data sparsity issues. Second, task adaptive sparse update is effective in identifying important layers and channels on the fly, thereby ensuring dynamic layer and channel update during deployment. Thank you for listening. If you have any questions, please reach out to me through this email. Thank you.